Okay, I'm starting. Okay. Let me share my screen. Okay. Today we'll start with last time we have done all the problems with flat plates, I mean external flows. Today we'll do with uh, internal flows inside tube. Okay. So let us first see what all are the just a brief on the formulas. So for fully developed flow, the temperature profile does not change. It remains similar. So del T by del X is equal to dTm by dx is equal to dTs by dx. So all this you know. So for constant flux, we have for constant flux problem dTm by dx is equal to minus Qs into perimeter divided by m dot Cp. Okay, for constant temperature, we have m dot Cp into dTm by dx is equal to minus Hp Ts minus Tm. Okay. Then this is the temperature. From here you get the temperature profile of the um, flow system. Then we also have this Q, Q convection delta T LMTD, where delta T LMTD is given by TO or TI. If TO is present before, then it should be ln delta TO divided by delta TI. So delta TO, delta TI is the temperature gradient at the outlet, temperature gradient at the inlet. Okay. So, and this AS is the surface area. So for pipe, it is usually pi dl. It is the surface area of the, this is the surface area of the tube. So it is usually pi dl for pipe. Then we have for calculating the heat transfer coefficient, we have to calculate this Nusselt number. So for Nusselt number, in Nusselt number is constant 4.36 for laminar flow. This is in the fully developed regime, okay? And this is for fully developed laminar and constant flux case. Nu is equal to 4.36. It's a constant. And for constant temperature case, constant temperature means the surface temperature. Nusselt number is given as 3.66. Then we also have some more correlations, some general correlations which can be used for constant surface temperature. This is not used much, but still you can write this for entry region, okay? For entry region. Not fully developed case, but for entry region. Is the constant temperature.
The Nusselt number equation is given in exam or not? We want to remember it or already given in exam?
You're asking, will this relation be given in the exam?
Yes.
I think it should be given, otherwise it's not possible to remember all this. And all these are not actually required. So mainly like the Dittus-Bolter equation, the ones which are very commonly used, those you can little bit by heart them. Okay, these all are not much required. These bigger ones, mostly it should be provided.
Okay.
Yeah. But in some cases like this cedar tate and all this, this is almost used for wide range of this uh, Prandtl number and wide range of this ratio. So this is very you can consider it common. I mean, you can use it for different, I mean, wide range of fluids. So this little bit you can by heart. I mean, this common ones, and the most common ones, if you go through the questions and all, then you can see this Colburn equation, and for turbulent conditions, Colburn and Dittus-Bolter, these are very commonly used. And there is not much difference between this Colburn and Dittus-Bolter also. So I will write it in a fresh page. And all these properties are evaluated at Tm, T mean temperature. That means average, almost you can consider it average. Mixing cup temperature. This is outside outlet temperature plus inlet temperature divided by 2. And for turbulent conditions, those were for laminar conditions. This is for turbulent conditions. There are mainly two correlations which are used. One is the Colburn equation is NUD is equal to 0.023 RE to the power 4 by 5 PR to the power 1 by 3. Okay, this Colburn equation is mainly used when Reynolds number is greater than 10,000, and also Prandtl number is 0.5 to around 3. Okay, when Prandtl number is from between 0.5 to 3, this is used. Another one is the Dittus-Boelter equation. These two are almost the same. 0.023 RE d to the power 4 by 5 PR to the power n. Only this changes n. So this is mainly used when Reynolds number is much greater than 10,000 and Prandtl number varies from 0.7 to 160. Okay, then we can start with the problems. These are some, mainly this will be used in the problems for turbulent conditions.
Ma'am, ma'am,
Yeah.
Dieter's Bolter equation PR to power n will be in condition
Oh,
when
yeah, yeah,
surface
yeah. N is zero point 0.4 for heating
yes, yes.
case. Sir has given, I think, Ts greater than Tm. That means the surface temperature is greater than the mean temperature. That means that is heating case only. And N is equal to zero point 0.3 for cooling. Ts is less than Tm. Yeah, so this is very important. By seeing the question, one should be able to tell which N should be used. Hmm. Okay, then this is the first question. Okay. In the final stages of production, a pharmaceutical is sterilized by heating it from 25 to 75 degrees Celsius as it moves at 0 0.2 meter per second through a straight, thin-walled stainless steel tube of 12.7 millimeter diameter. So it is a stainless steel tube. The diameter is 12.7, that means 0.0127 meter. And velocity is given as v is equal to 0 0.2 meter per second. The inlet temperature, that is Tmi, is given as 25 and the outlet temperature is 75. A uniform heat flux is maintained by an electric resistance heater wrapped around the outer surface of the tube. So this is a uniform heat flux case. And if the tube is 10-meter long, what is the required heat flux? If the fluid enters the tube with a fully developed velocity profile and a uniform temperature profile, what is the surface temperature at the tube exit? That means here what is Ts, surface temperature of the tube. Now first question they have asked, what is the heat flux? So for this first we have to uh, calculate what is the Reynolds number. Okay, for heat flux you don't require it. For heat flux there is a uh, this heat flux can be written as mcp delta T. Okay. This heat mcp delta T. This is not flux. Okay. mcp delta T gives the heat rate. So M was given as M was not given, right? But rho and all are okay. So rho and all are given. M means M dot means rho into V into volume, right? So volume can be written as this is M dot. That means mass rate, not a mass. If it was mass, then it can be directly written as rho into V, which can be written as rho into L into A. Okay, this is the volume. This is the volume, and this gives the volume. But since it is mass rate, instead of length, we are taking as the velocity. So this gives the mass rate. Okay, it is a mass rate. Rho is 1000, V is 0.2, and A is, here you have to take the cross section. That means pi d square, okay? Or pi d square by 4, not pi d square, pi r square or pi d square by 4. Since it is the volume of the tube, so you have to take it as a cross-sectional area. This cross-section. 3.14 into D is given as 0.0127. So how much it comes? It will come to be around 0.025. Okay, now you input this M here. So it is 0.025 into Cp is given as 4000 joule per kg Kelvin. And this temperature difference, what is this temperature difference? This is equal to the outlet minus inlet. So the outlet was 75 and the inlet is 25. So 75 minus 25 is 50. How much you get this?
5,000.
5000. Okay, so 5000 watt. This is the rate. Okay, now, but they have asked for what is the heat flux, not the heat rate. So you need, so what do you require here is area. You have to divide it by area. And what is the area here? It's not the cross section here because the heat transfer is taking place from the this surface like this. So you have to take the curved surface area, okay? That means pi dl. Network is disturbing a lot. Are you able to see my screen? Hello?
Screening not visible.
Are you able to see?
Yes, yes. Okay.
Okay. So so for for finding out the heat flux, we have found out the rate. For finding out the heat flux, we just need to divide by area. But the area will be not the cross section, but this time the area will be the curved surface area because the heat is getting transferred from the surface area, okay, not the cross section. So area is 5 dl. So q is 5000 and this is 3.14 into d is 0.0127 into length. Length was 10 meter long. So how much is this coming? How much is this coming?
It looks.
Yeah, heat flux. Just tell me directly which option. Coming out to around 12,538, right? Have you calculated how much it's coming? Hello, am I audible?
12538.24.
Yeah,
It's
so
mean option C.
yeah, yeah.
Option C.
Okay, okay. Then, if the fluid enters the tube with a fully developed velocity profile and a uniform temperature, what is the surface temperature at the tube exit? Already it is given it is fully developed, but if it is not given, how can you find out if it is fully developed or not? So x equal to 0.05 RE dPr into D. For laminar flow, okay, so how will you know whether it's laminar or not? For this, you need to first find out the RE. Okay, R is given by dV rho by mu. So D is 0.0127 into V is velocity 0.2, rho is 1000 divided by mu, 2 into 10 to the power minus 3. So if any chance, if by any chance this is not given, it's not fully developed velocity profile, if it is not given, then you can find out whether it's fully developed or not just by this uh, equation. So if it is more than the length, this pipe length, then it's not fully developed. But if the pipe length is greater than this, then it is fully developed. So, but for this you require RE, you require Prandtl number is already given, D is already given, so you need to find out Reynolds number. For laminar, this is the way to check. So if you find out the RE, how much it comes? This one,
1270.
how much?
1270.
1270. Yes, so it
Yes.
is laminar or turbulent?
Lemon.
Yeah, it's laminar. So for laminar, this is the way to check the fully developed condition. So 0.05 into 1270 into Prandtl number was given as 10. D is 0.0127. How much is this? It is around 8.06.
8.6.
Yeah, so it is more than or less than the tube length. Tube length was 10 meter, and this is 8,
Less than less.
less than. So it is fully developed. By the time the fluid reaches the whole length of the pipe, it is already fully developed. So for fully developed conditions, and also they have given everything actually. This Nusselt number they have already given. If it is not given also, you can consider it, because here I have already written for fully developed constant flux case, For laminar flow, it is Nusselt number is equal to 4.36. So if Nusselt number is equal to 4.36, then you can find out how much is H. H is equal to Nu Nusselt number into K divided by D. So K is how much here? K is 0.8, D is 0.0127, which is H. Then after you find out H, you can substitute Q double dash is equal to H into delta T. That is Ts minus at the end, right? So it should be TMO. They have asked to find out what is the surface temperature at the tube exit. That means tube exit is this TMO, and the gradient is Ts minus TMO. So just find out how much is T here. TSO only you have to find out. That is Ts. H is coming out to be around 274.6, right? How much is Q? Sorry, how much is Ts? Just find out surface temperature. How much is Ts?
120.65. It means 121.
Yeah. So C is the correct answer. It will come out
Yes.
to be around 121 degrees Celsius. Okay, we'll move to the next question. Water flowing at 2 kg per second through a 40 millimeter diameter tube is to be heated from 25 degree to 75 degree. So you understood the previous question, right? Because there were so many interruptions.
Yes, yes, I understand.
Okay. So this is 25 TMI. This is 75 TMO. By maintaining the tube surface temperature at 100 degrees Celsius. So this is constant temperature case, not constant flux. This constant temperature case because the tube surface is maintained at 100 degrees Celsius. Then water flowing at 2 kg per second means m dot is 2 kg per second. Diameter is 0.04 meter. What is the required tube length for these conditions? So This is the formula given for h bar already. Okay. Now first you have to find out what is this Re, because in this formula, for this formula, I mean this H formula, you're required to find out Re. PR is already given. PR is already given. You need to find out Re. Rest everything is given. So Re is given as, so Re is also given as 4m dot divided by pi d mu. Okay. Usually it is, if you expand it, how much it will come? M dot is rho into A into V, right? This is M dot divided by pi into D into mu. So 4 into rho into A. A is the cross section. Here the A is cross section because you are taking the volume. Okay, rho into volume, density into volume. So you need to take the cross section. When it is the case of heat transfer rate or heat flux, anything like that, since those heat transfer is taking place from the curved surface, the surface area of the tube, so that time it will be the curved surface, that is pi dl, but here it is pi d square by 4, pi d square by 4 into velocity, whole divided by pi into d into mu. So if you just insert all this, you will get dv rho by mu. So sometimes you can also use this formula also for Reynolds number. Okay, so if you calculate what is the Reynolds number, because directly you can substitute the values. M dot is given to 2 kg per second, pi d diameter is also given, and mu is also given here in the properties, so you can use this formula also. Instead, if you see here, if you use this dv rho by mu, you don't know what is v is not given here, the velocity of the fluid is not given, so it is better you use this formula, 4m dot divided by pi d mu. So how much you get Reynolds number?
116442.90.
116442.
42.90.
Okay. So for pi, obviously it is turbulent. Don't need to say anything.
Turbulent.
And already for turbulent, this is the formula. This is the Cedar. Sorry, what is this called? Ditus-Boelter equation. So it is heating case, right? So it is 0.4.
Yes.
So easily you can say this is the Ditus-Boelter equation. Now just calculate how much is H from here. K is given as 0.643 divided by diameter is given as 0.04 into Reynolds number is 116442.9 to the power 4 by 5 into Prandtl number is 3.56 to the power 0.4.
Three zero one seven 32.0137.
This is
32.
H.
Yes.
Sorry, there should be this term also 0.023. Did you calculate with this?
No, no, ma'am.
Uh,
Sorry, I'm not having.
yeah. I also did not write. Just follow this equation.
6939.83. Ma'am, I will join after 20 or 30 minutes. I want to go for some work. I
Uh,
love.
okay. But I have to continue with this. So we
Yes,
just
yes,
come,
of course.
we'll,
I will
yeah,
join.
continue wherever we are. Okay.
Yes, after 30 minutes, I will join.
Okay,
Okay.
okay, fine. So once we find out this age, uh, now what is required to find out the tube length for these conditions? The tube length means, so for finding out the tube length, we'll go for energy balance. So Q is given by mCp delta T. So Q is also equal to HA. LNTD. So delta T is actually TMU minus TMI. Now if I put um, so if you can, sorry, if we cancel this out, it should become mCp ln delta T naught divided by Ti is equal to H into pi dl. So L gives m dot Cp ln delta T naught divided by delta Ti whole divided by pi dh. Okay, so this gives 2 into 4181 ln delta T naught is Ts minus TMO. That is 100 minus 75. So this 25 and delta Ti is Ts minus TMI. So 100 minus 25. This is 75. So 3.14 diameter is how much? 0.04 into 6919. Sorry, 6939. So how much do we get here? We get almost 10.6 meter. So this is the length of the tube. So just by uh, equating the formulas of the heat rate, we can find out what is the length of the tube. So next question is, the atmospheric air enters a 10-meter long, 150 diameter uninsulated heating duct at 60 degrees Celsius. So this is the pipe. This is m dot equal to 0.4 kg per meter second. This is 10 meter long. This is 150 millimeter, that is 0.15 meter diameter. Enters the uninsulated heating duct at 60 degrees Celsius. That means TMI is equal to 60 degrees Celsius. Then Ts is given as 15 degrees Celsius. The duct surface is approximately constant at Ts equal to 15 degrees Celsius. What are the outlet air temperature and the heat rate Q for these conditions? Outlet air temperature. TMO you need to find out. And heat rate Q. So no correlation is given for this. So directly we'll find out what is the Reynolds number. First step, 4m by pi d mu. 4 into 0.4, 3.14 into diameter is 0.15 into mu. Mu is 189 into 10 to the power minus 7. So how much we get this? It will come to be around 17965, which is turbulent for tube. If it is turbulent, we can use the differential equation, and it is already given that it is uninsulated heating duct. That means it is a case of heating. So for in Dittus-Boelter equation, H is given as K by D into 0.023 into RED to the power 4 by 5 PR to the power 0.4. Now K is equal to 0.027 divided by diameter is 0.15 into 0.023 into RE is 17965 to the power 4 by 5 into Prandtl number to the power. Prandtl number is 0.706. How much we get this as? This will come out to be around 9.44 watt per meter square Kelvin. So what was asked for this question? The outlet temperature and the heat rate, that is TMO and Q. Okay. So first, from energy balance again, for constant, this is the constant temperature case. So we can write as ln delta T naught divided by delta Ti is equal to minus ASH H bar divided by MCP. So we can write it as delta T naught, that delta T naught divided by delta Ti is equal to exponential of minus A here is a surface area, so it should be pi dl into H bar, that is the average heat transfer coefficient, divided by MCP. Now delta T naught by delta Ti is Ts minus Tmo divided by Ts minus Tmi is equal to exponential of minus pi dl divided by mcp into h bar. Now ts minus tmo is equal to ts minus tmi into exponential of this minus pi dl divided by mcp into h bar. So what do we get here? We know surface temperature, we know the inlet temperature, and all these values we know. Pi, dl, h we found out, m, c, m we know, cp we know. So we can directly find out what is this tmo. So tmo is equal to ts plus all of this. So if this is considered this as a, so ts plus a, we get tmo. So if we substitute all the values, we get tmo as around 30 degrees Celsius. Okay, now next the overall from we already got the temperature, this tmo. Now to find out this heat rate q is then we can directly calculate this as h h a delta t, or also we can write mcp delta t, that is ts minus tmo tmi. So we get this as m is 0.4 into cp 1007 into ts minus tmi. Sorry, it should be tmo. Outlet temperature minus inlet temperature. So this is the overall heat balance. So TMO we found out as already 30 degrees Celsius. 30 minus TMI is 60. So what do we get this as? It is around 1212 watt, but in negative. Okay, so here the first option is the right answer. Now we move on to the next question. Here a liquid mercury at 0.5 kg per second is to be heated from 300 to 400 Kelvin by passing it through a 50 millimeter diameter tube whose surface is maintained at 450 Kelvin. So this is at the tube. Here the liquid mercury is flowing. M dot is equal to 0.5 kg per second. Then it is heated from 300 to, the TMI is 300 Kelvin. TMO is 400 Kelvin. Diameter is 0.05 meter. Surface temperature is 450 Kelvin. Calculate the required tube length by using an appropriate liquid metal convection heat transfer correlation. So here again we start with the correlation is already given here. So first for using this correlation, we need to find out what is the packlet number PED. So PED is given by RE into PR. So again, we need to find out what is this RE is 4M into pi D into mu. So this is given as 4 into 0.5 divided by 3.14 into D. D is how much? 0.05 into mu is 0.1309 into 10 to the power minus 2. Okay, so how much we get this RS? This R can be calculated. It comes out to be around 9727. So we can now calculate what is the PED. This is equal to 9727 into PR. Prandtl number is 0.0196. So how much we get this as? 190.64. That means almost 191. Okay, now once we get this packlet number PED, we can calculate the heat transfer coefficient. H is equal to K by D into 5 plus 0.025 to ED to the power 0.8. Okay, so K is given as 9.18. 9.18. Then D is 0.05 into 5 plus 0.025 into packlet number is 191. 191 to the power 0.8. So if we calculate it, how much we get it? We get it around 1224 watt per meter square Kelvin. So what was the question asked? The question was asked to find out the required tube length by using an appropriate. Okay. So we need to find out the tube length. So for finding out the tube length, again, the energy balance is used. Just like the previous question, we can directly calculate the length as mcp ln delta T naught minus Ti divided by pi dh. this average, this average. Now if we substitute all the values, M is 0.5 into CP. CP is 137.7 into ln delta T naught minus, delta T naught by delta Ti. So delta T naught is 450 minus 400. Delta Ti is 450 minus 300, which comes out to be around 150 Kelvin. Okay, so delta T naught is 50 divided by 150. So pi is 3.14, D is 0.05 into H. H has we have calculated to be around 1224. So it comes out around 0.393 meter. So the first option is the correct one. Okay, we'll move to the next question. The next question reads as the core of a high temperature gas cooled nuclear reactor has coolant tubes of 20 millimeter diameter and 780 millimeter length. So the coolant tubes is 0.02 meter diameter and this is 0.78 meter length. Helium enters at 600 Kelvin and exits at 1000 Kelvin. When the flow rate is 8 into 10 to the power minus 3, m dot is 8 into 10 to the power minus 3 kg per second. Determine the uniform heat wall surface temperature for these conditions. So how much is Ts? So this is uniform, that means constant wall, constant temperature case. So again we find out the Reynolds number. Reynolds number is calculated as 4m divided by um, pi d mu. So 4 into 8 into 10 to the power minus 3 divided by 3.14 into diameter is 0.02 into mu. Mu is 382 into 10 to the power minus 7. So if we calculate it, it will come out to be 1.33 into 10 to the power 4. So this is turbulent. So either we need to use the Dittus Bolter or Colburn. But here they have given this Prandtl number as 0.654. So usually for such Prandtl number, we have to use the Colburn. So it is less than 0.7. So we have the Colburn is preferred in this case. Colburn equation. So in Colburn equation, the formula is just Prandtl number to the power 1 by 3. 0.023 into 10 to the power 3. So K is 0.304 divided by diameter is 0.02 into 0.23 into RE. RE is 1.33 into 10 to the power 4 to the power 4 by 5 into Prandtl is 0.654 to the power 1 by 3. How much we get it as? 0.304 divided by 0.02 into 8 heat transfer coefficient as 604.18 watt per meter square Kelvin. Now they have asked to find out what is the uniform of the wall surface temperature. So we know Ts minus Tm naught divided by Ts minus Tmi is equal to exponential of minus ESH divided by m dot Cp. So here this TS we need to find out. TMO and TMI we know. So TS minus TM naught is 1000 divided by TS minus 600 is equal to exponential of minus 3.14 into diameter is 0.02, length is 0.78 divided by m was 8 into 10 to the power minus 3 into Cp is 3. This is into H. H is, we have calculated it as 604. So how much we get it as? I have done some mistake here. This is code 8. This is 0.49 around. So if we calculate it, so TS will come out to be 705.61 divided by 51. So it's 0.51. So it should come out to be 1383. Okay. So it was 1 minus 0.49, which comes out to be 0.51. So if we just and if we take 1000 there, 1000 minus 294.39 is this. So TS will be 705.61 divided by 0.51. Okay. So moving to the next question, we see the water at 27 degrees Celsius flows with a mean velocity of 1 meter per second through a 1 kilometer long pipe of 0.25 meter inside diameter. So we have this tube and the DI is 0.25 diameter, and the mean velocity is 1 meter per second through a 1 kilometer long pipe. Consider the pipe surface to be smooth. Now first determine the pressure drop, that is delta P, and power requirement, that is P. Okay, this is pressure, this is power. And we have to use a certain this data. Then note that friction factor F is a function of the tube surface condition. Even for a tube with smooth surface, even if it is smooth, there are different expressions to determine friction factor F depending on the Reynolds number of the flow. So, following expression can be used for a large range of Reynolds number. For that, first we find out what is the Reynolds number. Reynolds number is equal to V into D divided by nu. So V is 1 meter per second into diameter is 0.25 divided by nu. Nu is 0.8576 into 10 to the power 6. So if we calculate this, we get as 0.25 divided by 0.8575. So if Reynolds number is between 3000 to 5 into 10 to the power minus 6, so this number falls between this range. So we can take this expression. This is the expression for F, that is friction factor. So we have to calculate this F. F is equal to 0.790 ln RE minus 1.64 4 to the power minus 2, and RE is 0.29 into 10 to the power minus 6. So we can calculate this F as 0.790 into ln 0.29 into 10 to the power minus 6 minus 1.64 4 to the power minus 2. This should come out to be around 0.0145. Now we know this friction factor is equal to minus dp dx into d divided by rho square divided by 2. So this is the formula for friction factor. Now Now if I take this denominator here, F into rho square divided by 2, when I bring the d here, then dt by dx. So we can integrate it. So if we integrate it from 0 to L, means the length of the tube, we get this as delta P is equal to F by 2d rho square into L. We can calculate it as 0.0145 divided by 2 into D is 0.25 into rho 997 into square, that is 1 square. Is 1 into L, that is 1000, 1 kilometer, 1000 meter. Okay, so once we calculate the pressure drop, we can calculate the power as delta P into area into or velocity, P into volumetric flow rate. So delta P is 28913 into area is pi d square by 4, so 3.14 into, this is the cross sectional area, because here we are taking the volumetric flow rate, 0.25 square into is 1. If we calculate it, we get 1418 watt, or 1.42 kilowatt, also you can write. So we just directly uh, take the formula for the friction factor, which is given as this. Friction factor is also given as minus dp dx into d divided by rho square by 2. So from here we can calculate the delta p when the as we go along the flow, the pressure is decreasing, that's why there is minus here. So because the flow always takes takes place from higher pressure to lower pressure. So that's minus here, negative sign. And once we get this delta P by doing the integration, then we can also calculate the power which is given by delta P into the volumetric flow rate. So it is given as this, and it is calculated to be around 1.42 kilowatt for this question. Now, in this question, in a particular application involving fluid flow at a rate m dot through a circular tube of length L and diameter d, the surface heat flux is known to have a sinusoidal variation with x, which is of the form Qs x is equal to Qsm sine of pi x divided by L. So this Qsm is the maximum flux. Qsm is the maximum flux is a known constant, and the fluid enters the tube at a known temperature Tmi. This is known, and the maximum flux is also known constant. Assuming the convection coefficient to be constant, how do the mean temperature of the fluid and the surface temperature vary with x? That means mean temperature is Tm and surface temperature is Ts. How do they vary with x? So this question was already discussed in the class, in the lecture notes. So we just revise it again. So we know that dTm by dx is equal to Qs double dash into P perimeter divided by m dot Cp. Now this perimeter is given as perimeter is of the this cross section, perimeter of the cross section, that is 2 pi r or pi d. So we can write pi d divided by m dot Cp into this Q s double dash is given as Qsm sine pi x by L. Now to find out how this Tm varies with x, we have to find out the profile. So for finding out the profile, just integrate it. Delta Tm, this whole thing is constant already. Okay, when x is 0, T is the entrance, that is Tmi. When x starts from here to here, so here x is equal to 0, here x is equal to L. So when x is equal to 0, T is equal to Tmi, x is equal to L, T is equal to Tm naught. So if it varies from 0 to L, if x varies from 0 to L, Tm will vary from Tmi to Tm naught. Okay. So in the left hand side we get Tm naught minus Tmi is equal to pi d divided by mCp. Now if we integrate it, integration of sine x is minus cos x. So divided by pi by L. Minus sign is there. Cos pi x by L. Okay, from 0 to L. Now if I write it in the next page, pi will get cancelled. Okay, so LD divided by MCP. This keep as this is constant. Maximum flux is a known constant. So we can take this out. Okay, so we need to find out what is the variation with this Tm with x, right? So we just take it to a inter some value in the middle. Instead of taking the whole length, we can take it at some as x, and we will take it the temperature as Tm. Mean temperature. Okay, is Tm. So instead of T naught, we can write it as Tm. And here we can write it as x. So here also it should be Tm minus of minus it will become, so it will be cos plus cos 0. So it will be 1 minus cos pi x by L. So if it is Tm, we can write it as plus Tmi. So this is how it varies, how the mean temperature varies with x. Now again we have to find out how this Ts varies with x. Now for Ts is related with Tm as Q is equal to H A Ts minus Tm. Or if we write the flux Q double dash, then A is gone, H Ts minus Tm. So we can write it as Ts is equal to Q double dash by H plus Tm. Now this is equal to Tm is this whole one, and Q double dash is this Qs sin x by L, sin pi x by L divided by H plus Tm is Ld by Mcp 1 minus cos pi x by L plus Tmi. Okay. So this is how Ts varies with x. So in the options they have given only for Ts. So the option will be this last option. Ts is equal to qsm by h sine pi x divided by L, this one, plus tmi plus ld qsm by mcp into 1 minus cos pi x by L. Okay, now uh, with the basis of this question only, we can, the question is extended more. Water at a flow rate of mass is equal to 0, mass flow rate is equal to 0.22 kg per second is cooled from 70 degree to 30 degree by passing it through a thin walled tube of diameter d equal to 50 millimeter. So diameter is given as, so this is the 0.05 meter. Inlet is 70 degree, outlet is 30 degree. It is the cooling process. Now mass is, how much mass is entering? 0.22 kg per second. And the coolant is 15 degrees Celsius in cross flow over the tube. That means inside the tube, the coolant is flowing. So what is the required tube length if the coolant is air and its velocity is v equal to 20 meter per second? And the next is, what is the tube length if the coolant is water and v is equal to 2 meter per second? So first we calculate the Reynolds number of the, we have to separately calculate for the inside tube, inside fluid and outside fluid. So first Reynolds number of the inside tube, so inside fluid, we calculate as di 4m divided by pi d mu. So 4 into m dot is 0.22 divided by 3.14 into, here since we are calculating for the inside fluid, so we'll take di inside diameter as, okay, already it's one diameter only, so 0.05 is the diameter into mu is, so mu is, it is inside fluid is water, so we have to take water. For water it is 548 into 10 to the power minus 6 Newton second per meter square. So we have to calculate all this at the mean temperature or the mixing cup temperature. So that is 70 plus 30 divided by 2 is equal to 50 degrees Celsius. So these properties are given at 50 degrees Celsius. So we'll take this mu 548 into 10 to the power minus 6. So we can calculate this as, so it will come out to be around 10223. And then for the outside fluid, we have to calculate the RD naught. RED naught is equal to, since mass flow rate and all are not given, but the velocity is given. Velocity is given as 20 meter per second. The coolant air, that means the outside fluid. So we calculate it as V into D by mu. So it is 20 meter per second into D is 0.05 and nu is, for air it is 15.89 into 10 to the power minus 6. So we get this as 62933. Now we have to calculate the respective H for the inner and outer fluid, HI and H naught. So for this, for inner inside the tube, we calculate it from, since it is turbulent, we can calculate it from the Dittus bolter, that is NU DI, or directly you can calculate the HI. This is K by D into 0.023 into RE to the power 4 by 5 Prandtl number to the power. For cooling it is 0.3. So if we substitute the values here, we get this HIS 692.4 watt per meter square Kelvin. And for H naught, for calculating the H naught, we use the, for this is Dittus bolter equation. And for outside fluid, we have to use the Churchill-Bernstein correlation. This is for outside external fluid. This is some general correlation. AF by D into this whole one is 0.3 plus the very big equation, 0.62 into RED to the power half Prandtl number to the power 1/3 1 plus 0.4 divided by PR to the power 2 by 3 whole to the power 1 by 4, then 1 plus RED divided by 282,000 to the power 5 by 4 whole to the power 4 by 3. So if we input all the values here, so this is for the outside one. So note we have to insert all the values for the outside fluid. So we get this around 158.7 watt per meter square Kelvin. Okay, sorry, this is Nusselt number. Heat transfer coefficient we get as 83.5. Now we have to find out overall coefficient, which we can find out as 1 by Hi plus 1 by H naught. So from here, we get this 74.51 watt per meter square Kelvin. Then we can calculate the length as L can be found out from Q is equal to overall heat transfer coefficient into H into AS into delta T LMTD. So we also need to find out what is this delta T LMTD. It is given by delta T naught minus delta Ti divided by ln of delta T naught by delta Ti. So if we put this, we can also split this AS by DL. Okay, and this Q we can find out from the overall Q, that is MCP delta T. So from where we from if we input all this, calculate all these values and input substitute this, then we can calculate this L. Okay, which we can find out to be around 100 meter. Okay, so we'll continue this in the next class, how this detailed calculation. For today we stop here. Thank you.